Uses of coils in electronics. Inductive sensors are a type of proximity sensor used to detect the presence or absence of metallic objects within their sensing range. They work based on the principle of electromagnetic induction. The basic operation of an inductive sensor involves an oscillating electromagnetic field generated by an induction coil within the sensor. When a metallic object enters the sensing range of the sensor, it disturbs the electromagnetic field, causing a change in the inductance of the coil. This change is detected by the sensor, which then triggers an output signal to indicate the presence of the object. Here are a few key points about inductive sensors. Sensing range. Inductive sensors have a limited sensing range, typically ranging from a few millimeters to several centimeters. The sensing range depends on the size and material of the target object. The sensing range of an inductive sensor refers to the distance at which it can detect the presence of a metallic object. It determines the maximum distance between the sensor and the target object for reliable detection. The sensing range of inductive sensors can vary depending on several factors, including the design of the sensor, the size and material of the target object, and the operating frequency of the sensor's electromagnetic field. Typically, the sensing range ranges from a few millimeters to several centimeters. Smaller inductive sensors with a lower operating frequency generally have a shorter sensing range, often in the range of a few millimeters. These sensors are suitable for applications where close proximity detection is required, such as detecting small metal components on a production line. Larger inductive sensors with a higher operating frequency can have a longer sensing range, reaching several centimeters. These sensors are used for applications that require detection over a larger distance, such as detecting the presence of larger metal objects or controlling the position of machinery. It's important to note that the sensing range is influenced by factors such as the size and material of the target object. Larger or more conductive metallic objects can be detected at greater distances compared to smaller or less conductive objects. When selecting an inductive sensor for a specific application, it is crucial to consider the desired sensing range in order to ensure reliable and accurate detection of the target objects. The manufacturer's specifications for the sensor should provide information on its sensing range under different conditions, allowing you to choose the most suitable sensor for your needs. Target objects. Inductive sensors are primarily used to detect metallic objects such as ferrous and non-ferrous metals. Non-metallic objects, such as plastics or liquids, do not significantly affect the sensor's electromagnetic field and are usually not detected. The target objects for inductive sensors are primarily metallic objects. These sensors are specifically designed to detect the presence or absence of metal within their sensing range. Inductive sensors can detect both ferrous and non-ferrous metals. Ferrous metals contain iron and are magnetic, while non-ferrous metals do not contain iron and are typically non-magnetic. Examples of ferrous metals include iron, steel, and nickel, while examples of non-ferrous metals include aluminum, copper, brass, and stainless steel. It's important to note that inductive sensors are not typically suited for detecting non-metallic objects. Non-metallic objects, such as plastics, wood, glass, liquids, or paper, do not significantly affect the sensor's electromagnetic field and are usually not detected by inductive sensors. The ability of inductive sensors to detect different types of metals depends on factors such as the sensor's design, operating frequency, and sensitivity. Some sensors may have limitations in detecting specific types of metals or may have different detection ranges for different metals. When using inductive sensors, it's important to consider the composition and properties of the target objects to ensure accurate and reliable detection. The size, shape, and material of the metallic objects can affect the sensor's performance and should be taken into account when selecting an appropriate sensor for a specific application. Output signals. Inductive sensors can provide either analog or digital output signals. Digital sensors typically provide a binary signal, on/off, to indicate the presence or absence of a metallic object. Analog sensors can provide a continuous output signal that varies based on the distance or size of the detected object. Inductive sensors can provide different types of output signals to indicate the presence or absence of a metallic object within their sensing range. The two primary types of output signals are digital and analog. Digital output signals, digital inductive sensors provide a binary signal, often referred to as an on-off signal or a switch signal. When a metallic object is detected within the sensor's sensing range, the output signal switches from one state, off, to another state, on, to indicate the presence of the object. This type of output signal is commonly used for simple presence/absence detection applications. Analog output signals, analog inductive sensors provide a continuous output signal that varies based on the distance or size of the detected metallic object. The output signal is typically a voltage or current that corresponds to the proximity of the object to the sensor. The magnitude of the output signal increases as the object gets closer to the sensor. This type of output signal is used for applications that require more precise position sensing or distance measurement. The choice between digital and analog output signals depends on the specific requirements of the application. Digital signals are suitable for simple presence/absence detection tasks where a binary indication is sufficient. Analog signals, on the other hand, provide more detailed information about the proximity or distance of the detected object and are suitable for applications that require finer control or measurement. It's important to note that the output signals of inductive sensors are designed to interface with other devices or systems. These signals can be connected to programmable logic controllers, PLCs, microcontrollers, or other control devices to trigger further actions or to provide feedback in automated processes. Manufacturers of inductive sensors usually provide information on the type of output signal and its specifications in the sensor's documentation or datasheet, allowing users to select the appropriate sensor for their specific application and integration requirements. Applications: inductive sensors find wide applications in various industries, including manufacturing, automotive, packaging, and material handling. They are commonly used for object detection, position sensing, and automation processes. For example, they can be used to detect the presence of metal parts on a conveyor belt or to control the position of robotic arms. Inductive sensors have a wide range of applications in various industries. Here are some common applications where inductive sensors are utilized. Object detection: inductive sensors are widely used for detecting the presence or absence of metallic objects in industrial automation systems. They can be employed in conveyor systems to detect the presence of metal parts or components for sorting, counting, or quality control purposes. Position sensing: inductive sensors are utilized for position sensing tasks where the precise location of a metallic object needs to be determined. For example, in assembly lines, inductive sensors can be used to verify the correct positioning of metal components before the next step of the assembly process. Machine tooling: in machine tooling applications, inductive sensors are used to monitor the position of cutting tools or workpieces. They ensure that the tool is properly aligned or that the workpiece is correctly positioned before machining operations are initiated. Robotics and automation: inductive sensors play a vital role in robotics and automated systems. They are used to provide feedback for robot positioning, object detection, and collision avoidance. By detecting the presence or absence of metal objects, inductive sensors help robots navigate and interact with their environment. Packaging and material handling: in packaging and material handling industries, inductive sensors are employed to detect the presence of metallic containers, caps, or packaging materials on conveyor belts. This enables accurate sorting, filling, or packaging operations. Automotive applications: inductive sensors are extensively used in the automotive industry. They can be found in applications such as wheel speed sensing for anti-lock braking systems, ABS, gear position sensing, proximity detection for automatic doors, or engine position sensing for ignition timing. Security systems: inductive sensors are utilized in security systems to detect the opening or closing of metallic doors, gates, or windows. They are integrated into alarm systems to trigger alerts when unauthorized access is detected. Proximity switching: inductive sensors serve as proximity switches for various applications. They are used to control the operation of machines, equipment, or devices based on the presence or absence of metallic objects. These are just a few examples of the many applications of inductive sensors. Their reliability, durability, and ability to detect metallic objects make them suitable for a wide range of industrial and automation tasks. Advantages: inductive sensors offer several advantages, including high reliability, fast response times, and resistance to harsh environments. They are not affected by factors such as color, transparency, or ambient light, which can be limitations for other types of sensors like optical sensors. Inductive sensors offer several advantages that make them widely used in various industrial applications. Here are some of the key advantages of inductive sensors. Reliability: inductive sensors are known for their high reliability. They have a robust construction and are designed to withstand harsh industrial environments, including vibrations, temperature variations, and moisture. This reliability ensures consistent and accurate detection of metallic objects over long periods of operation. Non-contact operation: inductive sensors operate without physical contact with the target objects. This non-contact operation eliminates mechanical wear and tear, reducing the need for maintenance and increasing the sensor's lifespan. It also prevents damage to delicate or moving objects. Fast response time: inductive sensors have a fast response time, typically in the range of microseconds. This quick detection and response enable high-speed automation and control processes, contributing to increased productivity and efficiency in industrial applications. Immunity to environmental factors: inductive sensors are not affected by factors such as color, transparency, or ambient light conditions. They operate based on electromagnetic induction and are not influenced by the optical properties of the target objects or the surrounding environment. This immunity to environmental factors ensures reliable detection in various lighting conditions and reduces false readings. Wide operating temperature range: inductive sensors can operate over a wide temperature range, allowing their use in both hot and cold environments. They are suitable for applications where extreme temperatures are encountered, such as automotive manufacturing or industrial processes involving heating or cooling. Easy integration: inductive sensors are relatively easy to integrate into existing systems or machinery. They usually have standard electrical interfaces, making it straightforward to connect them to programmable logic controllers, PLCs, or other control devices. Additionally, they can be easily mounted and adjusted for optimal positioning. Cost-effective: inductive sensors are often considered cost-effective solutions for object detection and position sensing tasks. They offer a good balance between performance and affordability, making them a popular choice in various industries. Overall, the advantages of inductive sensors, including reliability, non-contact operation, fast response time, immunity to environmental factors, wide operating temperature range, easy integration, and cost-effectiveness, contribute to their widespread use in industrial automation, manufacturing, and other applications. Limitations: since inductive sensors rely on the presence of metal, they are not suitable for detecting non-metallic objects. Additionally, their sensing range is limited, and the detection accuracy may be influenced by the size, shape, and material of the target object. While inductive sensors have many advantages, they also have some limitations that should be taken into consideration for specific applications. Here are some of the limitations of inductive sensors. Limited to metallic objects: inductive sensors are designed to detect metallic objects and are not suitable for detecting non-metallic materials such as plastics, wood, or liquids. If the application requires the detection of non-metallic objects, alternative sensing technologies, such as capacitive or optical sensors, may be more appropriate. Limited sensing range: inductive sensors have a limited sensing range, typically ranging from a few millimeters to several centimeters. The sensing range depends on the size and material of the target object. Objects outside this range may not be detected reliably. For applications requiring detection at larger distances, other sensing technologies like ultrasonic sensors or laser sensors might be more suitable. Influence of material properties: the detection range and accuracy of inductive sensors can be influenced by the material properties of the target object. Different metals have varying conductivities, and the sensor's performance may differ when detecting objects made of different metals. Additionally, factors such as the shape, size, and surface finish of the object can affect detection accuracy. Environmental interference. Inductive sensors can be susceptible to interference from external electromagnetic fields or metal structures in the surrounding environment. Strong magnetic fields or nearby conductive materials can affect the sensor's performance and cause false readings or reduced sensitivity. Care should be taken to minimize such interference in the application environment. Limited position sensing accuracy. While inductive sensors can provide proximity or presence detection, their ability to provide precise position sensing may be limited. They can indicate the presence or absence of an object but may not provide fine-grained positional feedback. For applications requiring precise position sensing, alternative technologies such as linear encoders or laser displacement sensors may be more suitable. Size limitations. Inductive sensors come in various sizes, but their physical dimensions may limit their use in certain applications with space constraints. The size of the sensor may affect its mounting options or integration into compact machinery. It's important to carefully evaluate these limitations in the context of the specific application requirements and select the most appropriate sensing technology accordingly. Overall, inductive sensors are widely used for their robustness, reliability, and suitability for detecting metallic objects in industrial applications.